just math আসছে কিছু আসে না, theory খুবই কম, so there'll be a lot of math to tackle, some very complicated math as well. Okay, so we saw what was specific capacity. Specific capacity is the amount of energy needed to raise the temperature of 1 kg substance by 1 degree Celsius or 1 Kelvin, and this is the formula. You had this in your O levels, right? So same জিনিস, কোনো কিছু different না এখানে. Just remember that it's the change that you're finding. Okay, whenever you use the formula, it's always the change value. Okay. Right, so let's see what kind of questions to expect, because as I just mentioned, it's mostly math related. So I'm not sure. Question we'll start from easy and we'll move on to difficult. Okay. All right, so these are questions that you get in your exam. So right, so the first type of question that you get is regarding something called thermal equilibrium. So you can use specific heat capacity to figure out when can you attain thermal equilibrium. So the question would be something like this. You have a container here, and this container contains a liquid at room temperature. So that's the container that you have here, and there's a liquid inside this. Now it turns out that this liquid is at room temperature, so it হচ্ছে 25 degrees Celsius. That's the temperature value, 25 degrees Celsius, and mass হচ্ছে 2 kilograms. So you have this container with this liquid. Okay, now what we're going to do is we will pour liquid into this container, another liquid, and that liquid is obviously at a different temperature. What you need to figure out is what is the final temperature of the mixture. So I'm making the যেটা করব, I'll take this liquid that's in this container, right, and I'll pour this liquid into the other container. So this liquid that you have in this container is at a higher temperature. Same liquid, they're both are water, by the way. Okay, so this one is at 90 degrees Celsius. So this is 90 degrees Celsius water, almost boiling, and 400 grams of liquid. Okay, by the way, do you know what's the link between grams and liters and milliliters for water? It's 1:1. Okay, I think that 1 gram is how much ml? 1 ml. Okay, why is that so? It's because density of water is what? 1. So 1 gram is actually equal to 1 ml, given that it is pure water. Okay, if it's impure, then the ratio can vary. Anyway, so this is the setup here. So you pour the water into the container, and as you pour the water into the container, what is the final temperature of the mixture? So final temperature very good of it. Now, how do you solve this? I'll give you a hint first, then I'll give you some questions to try out. So can you tell me, when something attains thermal equilibrium, what is the criteria that needs to be fulfilled? Yeah, so the thing is, for thermal equilibrium, requirement loki dekhi. So thermal equilibrium. We discussed this before, but we discussed this as a theory. We didn't do any math. Now we can do the math. So first requirement হচ্ছে both systems attain what? Attain same temperature, which means that their average K is going to be same. Our second target is very obvious here, which is energy gained must be equal to what? Energy loss. This is the important part. Okay, so always one system is going to gain energy and the other system is going to lose energy. So in any kind of equilibrium scenario that you have, there's a system that gains energy and there's always a system that loses energy. So in this particular scenario, okay, so can you tell me which one loses energy, the 90-degree one or the 25-degree one? 90. So this one loses energy. And obviously, because you're pouring it into the other one, this one gains energy. Now, they will continue to lose energy and gain energy until what happens? Both of them attain what temperature? Same temperature. So how do you, mention that? So that 90 will actually go down and the 25 will actually go up. And they both will meet what temperature? Common temperature. So this is the common final temperature, right? So once you have this information, you can use this to find your final temperature. Try it for this, but do. So what is the final temperature of the mixture? So if you mix these two liquids, final temperature of the liquid. Question did you understand the concept? You mix the two liquids, they lose energy, they gain energy, and eventually they both will reach a common final temperature. And that common final temperature is your, the equilibrium temperature. Technically, aren't both of them losing energy to the atmosphere? Yes, this is a closed system. So generally speaking, you'll find that the final temperature is not actually the one you calculated. It's a little different. Often they'll ask you why, and that's when you say that probably lost the surrounding. Okay, so a question out the two similar liquids are mixed, having different initial temperatures. What is the final temperature of the mixture? Is that correct? So, how do you approach this? So what do you write here? So first, this is how your statement should be. When thermal equilibrium is attained, thermal energy data should be equal to energy lost. What's the formula for gain in thermal energy or loss in thermal energy? MC del T, right? So that's going to be MC del T should be equal to also MC del T because gain and loss. What's the energy gain? So we'll just focus on this system here, okay? The container here. So what's the energy gained here? So mass of 2 kilogram, and what is the specific heat capacity of this? I didn't tell you what liquid it is, right? So you can just consider it to be C of liquid. And what is my initial temperature? 25. What's the final temperature it attains? T. So what's my change in temperature? Should it be 25 minus T or T minus 25? T minus 25. Okay, so এখানে একটা জিনিস add করে রাখবো পাশে. There are mass কত 2 into specific capacity C of liquid, which we do not know, into change in temperature. Always go for the big one minus the small one because we want a positive change, right? So T minus 25 এখানে হবে এটা পাশে অ্যাড করে দিচ্ছি for change in temperature. Always find the positive difference. Bracket higher T minus lower T. Right, so that is that. So what should be my other part? On side ki hobe? Again, same thing, but what's the mass going to be this time? Is the mass going to be 400, or do I need to convert this? Convert, right? So what should that be? 400 divided by 1000, because you need it to be in kilograms, into again C of liquid, because we're mixing the same liquid. C of liquid into what is the change in temperature this time around? 90 minus T, because it's a higher to lower, right? So you can think you'll find out that the specific capacity of the liquid cancels out, right? And you have this T that you need to solve for. Theta কত আসলে দেখব একটু। $30. You got 57.5. That's the actual answer. আচ্ছা তোমরা করে দেখো কি হয় এখানে। So 2 into T minus 25 and 0.4 into 90 minus T. As you solve that, you'll get your value. কত আসে? 35.9. আচ্ছা, so 35.9 degrees Celsius. That's the final temperature. Do you understand the process? So how do you solve these kind of questions? The process when it's in equilibrium, this is what you do, okay? So when solving questions about attaining equilibrium, we equate the change in gain and loss in energy of the two systems, and then find the final temperature. $35.8. Okay, so do you understand the concept of equilibrium? I'll show this one more time. So if you're mixing two systems, this can be liquid, this can be solid liquid, on variation exists for actually. But if you're mixing two liquids, what happens is that they will, mix around, the energy will dissipate and the energy will transfer until both of them have the same temperature. Because if they both have the same temperature, then energy transfer doesn't take place, net energy doesn't take place, right? So we're taking something that is 90 degree at and 400 grams and mixing it with 25 degree 2 kg. So imagine you have a bucket of water and you're pouring like a glass of hot water into it. That's basically it, right? So if your bucket of water is 25 degrees Celsius, if you pour like boiling water into it, what's the final temperature that you get, right? So how do you solve this thing? So when it comes to equilibrium questions, there is only one thing that you need to be careful about, that they both must attain what temperature at the end? Same. And it is achieved through one system gaining energy and the other system losing energy. That's how it works, right? So who's going to gain energy? Obviously the one at lower temperature. And who's going to lose energy? The one at higher temperature. And there's a formula that tells you how to find gain or loss in energy, thermal energy. What is that formula? MC del T. That's the theme of this chapter, right? Last class with Excel. So if you find the increase in temperature, it'll tell you how much heat you need to provide. If you find a decrease in temperature, it'll tell you how much heat you need to remove. Okay, so that's the process. So what we did is we found the energy gained by the system. How? MC del T. Final temperature is T, initial temperature is 25. So I take T minus 25 because for change in temperature, we always find a positive difference, higher minus lower. Okay, so this is because it's energy value and positive hot is safer. And for loss, who's losing energy? This one, right? So what should it be? MC del T. So MC is the same liquid, so same specific capacity, into 90 minus T, because obviously 90 is going to be higher than that temperature. Once you equate these two, you find that temperature is 35.8 degrees Celsius. This is obviously provided that no energy has been lost to the surrounding. Okay, so that is something that may happen. Okay, so if you think that Parba, our question did she? Just keep in mind, ask আমরা সব specific heat capacity related questions করবো. It's mostly math. Okay, so we'll start with this one. Later, we'll look into something called latent heat of fusion and vaporization, and then we can do all the questions out there. So আমি একটা দিচ্ছি তোমাদেরকে একটু try করার জন্য, see if you can answer this. So similar scenario. Okay, it's a red hot iron sphere. It's like very high temperature, 200 degrees Celsius when it's being heated for a long time. And you have water here at 20 degrees Celsius. So you're going to drop this iron sphere into the water. You need to find out what happens to the water. What temperature does it attain? Okay, so the iron sphere that you have here is 40 grams, like very small sphere. Okay, 40 grams. And the water in the bucket is 2 kilograms like before. So তোমাদেরকে figure out করতে হবে as you drop this into the container, what is the final temperature that the system attains. Okay, specific capacity of water is given. You have to know this, by the way, 4200 joule per kg per Kelvin, and specific capacity of iron হচ্ছে 900 joule per kg per Kelvin. Right. So find the final temperature attained. $28.76. 20.8. That's right. So the iron sphere is dropped into the bucket of water. The initial temperature of the sphere is 200 degrees Celsius, and the final temperature, initial temperature of water is this. Find the final temperature attained of the system, 20.8. 20.8. Okay, let's solve this. So how do you do this? At equilibrium, common temperature আমরা নিলাম হচ্ছে T. Common temperature attained is T. So how do we find that? So you find the energy in energy gained is equal to energy lost. Energy gained here is by the iron sphere, so the water. So it's going to be mc water del T. And who's going to lose the energy here? The iron sphere. So mc iron times del T. Now mass of water is 2, specific capacity of water is 4200. Into change in temperature is going to be T minus 20 equals to mc del T. Mass is 40 divided by 1000. Right, so 40 divided by 1000 into specific capacity is how much? 900. Into change in temperature is going to be how much? 200 minus T. No. Okay, so I'll show you why. So yeah, once you solve this, you'll get your answer. It's 20.8, right? So 20.8 degrees Celsius. So why don't we need to convert into Kelvin despite our quantities provided in Kelvin? It's because change in temperature is what? Same in degrees Celsius and Kelvin. Let me explain, okay? So let's say you have 20 degrees Celsius and it is going to go to 50 degrees Celsius. What is the change in temperature here? Yeah, so that's very easy, 30 degrees Celsius. Now, if you want to find this in Kelvin, what you do is you convert 20 to Kelvin. So this is in degrees Celsius, this is in Kelvin. Kelvin is 293 Kelvin. And what is 50 degrees Celsius in Kelvin? 323. 323 Kelvin. What is the change in temperature once again? 30 Kelvin. So just remember that change is always the same because both are linear scales. Change is always the same in degrees Celsius and Kelvin scale. Yes, absolute value is different, but the change is always the same. Okay, so important. So yeah, that's how you get your answer. Okay. So additional question থাকতে পারে এখানে, as you know that there'll be always a question at the end that's theory based. They'll ask you, in reality, the water temperature doesn't rise as much. Why? Right, ওইটারও accept করে না. So they don't accept that anymore. It's not wrong, but they want to be more specific. Obviously, heat is lost to the surrounding, but you need to explain in what manner. So what do you think? So why is the change in temperature? Why is the increase in temperature not as calculated? Sometimes they'll ask, is it more or less? Okay, is it more or less than calculated? So this one I think you know, Kiyove. Yeah, so it is less than calculated. And reason to key? But surrounding is water, right? No, that's very minimal. Huh? But आगे तो water जाओगे. Huh? Vapor. Yes, what happens with vapor? Vapor. Vapor where? Evaporation is a slow process. Boil. Actually, you're right. So something that you'll notice, if you take a very hot object, right, and if you put it into the water, there'll be a fizz, like there'll be some steam coming out of it, right? But you'll notice that the water is still cold to touch. So why was there a steam? So what happens is the ball is very high temperature. The moment you place the ball in the water, the molecules that touch the ball instantly turn themselves into what? Gas. They go through the whole cycle. They go from 0 to 200 because the water molecules will show energy in it. So they themselves turn into what? Steam, and they escape. The rest of the energy is not available for the water, so the water temperature doesn't rise. So you'll find that they will take hot objects and place it in a cold liquid. There'll be some steam coming out of it, right? And they will liquid temperature change by it. It's just some of the gas has escaped. Okay, so in your exam you need to say that. I'll tell you why your answer such as energy loss to the surrounding is incorrect. Energy loss to the surrounding is the reason why you have equilibrium, right? I mean, equilibrium can also, you take the object and place it in the water. What is the surrounding of the object? Water. So it is normal. But the question is, water cannot energy gain for it because some of the energy was not transferred to the heat of water. It was rather used to change the state of water. And when you change the state of water, energy is taken away right from the object. There's no scope for energy to be given to the water to raise its temperature. If you say energy is lost to the container, why doesn't that make sense? Because when you place the ball in the water, who heats up first? Water. The water right temperature যাবে এরপরে তোমার temperature drop করবে, and that's because it's lost to the surrounding, lost to the container. But এখানে জিজ্ঞেস করছে 20.8 টা রিচই করবে না কেন? It's because not all the energy was used to raise temperature. Some of the energy was what? Used to boil the water. Therefore, not all the energy is available. Okay, so it's less than calculated. Reasonটা হচ্ছে when the ball is placed in the container, some of the right. ওইটা we haven't start করলাম না, তার জন্য এটা is good point here. So when the ball is placed in the container, some of the heat is used to turn the liquid into gas. Is used to turn the liquid to okay. So yeah, just go through this, then I'll start the heating cycle. It's relating to fusion and vaporization. Yeah, the water won't boil, only the surface will boil. So if you take this one here and put it in this place, right, what you'll notice is that around this object is what's showing up. The term they use in chemistry is effervescence, right? What is that? Bubbles, right? And that's basically what coming out, steam, just from the surface layer, okay? To do anything to the water. So all the energy was taken by the water molecules. So nothing is available for the water itself. So something changes here. This amount of water that's there, it obviously, because some of them have evaporated. Whatever water is left doesn't really have any energy to gain from the ball. That's the temperature right now. Right. Oh, why is 35.8 defined? Yeah, that's because they cannot say all the energy from here goes to the water, right? So first all the energy goes to the water, then the water heats up, and then what does the water do to the surrounding? Now, yes, if you were pouring this over a very long duration, then some of the heat may escape from there, and that's why you might have some loss. And in the exam, if you say energy is lost to the surrounding, they don't accept this anymore. So what you need to say is energy is lost to the surrounding in what manner? So you have to add that. Like in O levels, you could just say energy lost to the surrounding. In fact, nowadays even O levels don't allow it. So you need to be more specific. Energy lost to the surrounding as what? As heat to the air, or as radiation to the surrounding. That's how your answer would be. Okay. Right. So next there is an experiment, but Tarak Doche. Can you go to page 53? Oh, yeah. Yeah, if you're copying this, it's copied right now. And then we'll go to page 53. Yep. Okay, let's look at the heating graph. So the heating graph was part of O-level syllabus. They got rid of it. Now you have it in A-levels. So what is the heating graph? So the heating graph is, you need to understand what happens when you heat any substance, and they actually follow a very particular sequence of events. So we'll use water for example here. The y-axis is temperature in degrees Celsius, and the x-axis is going to be time. How are we heating this thing? So we are using a heater here. So we are providing heat in what manner? A consistent manner. Okay. So I will start the process by using an ice cube, like an ice block, a large ice block. And this ice block starts at a temperature of minus 20 degrees Celsius. So you start at a temperature here, minus 20 degrees Celsius. So it's a large ice cube. It's going to remain an ice cube right now because it's a very low temperature. And then what we do is we provide heat to this ice cube. Can you tell me, if you provide heat to this ice cube here, what will it do? Will it melt right away? No, right? So what will it do? It will raise its temperature. So देखो heat करते से temperature बढ़ते से minus 20, minus 19, minus 15, and बढ़ते से temperature, and the rise in temperature happens in a constant manner, and it keeps increasing, increasing, and then at a particular temperature, the rise in temperature stops. That is 0 degrees Celsius. So what is happening in this part? I'm going to get to break down for both of it. So can anyone tell me what is happening in this blue part in terms of molecular structure, molecular movement? What is happening? Right, exactly. So if I answer this in terms of internal energy, right, what do you think is happening to the internal energy from let's say A to B? The internal energy here, what is happening to it? Increases, right? So it's clear here that this is internal energy increases. And what is the equation for internal energy? The change equation, del U W. Acha, but there's another one with just internal energy. I'm going to tell you. What is it? Internal energy is a sum of what? Random K plus P, right? That's what internal energy is, right? Can you tell me here which one is changing? Is it the K or the P? K. Because there's a temperature rise. So K is increasing and P is what here? Constant. This is important, okay? So our K বাড়তেছে, but potential energy is remaining constant. And then what happens is the ice cube reaches 0 degrees Celsius. What do you think is the ice cube at 0 degrees Celsius? Is it liquid or is it solid? Solid, right? It's still solid here. So it starts off as a solid. But then I think you know this, that as you keep increasing temperature, what you'll start to notice is that তোমার temperature বাড়লে তোমার energy বাড়লে temperature বাড়ার কথা ছিল, but এখানে notice করো temperature বাড়াচ্ছ or energy বাড়াচ্ছ, temperature কি থাকে? Constant. Does anyone know why? Yeah, it's just called latent heat of fusion. So let me tell you what this term is if you haven't heard of this before. Latent heat is referred as hidden heat. And why is it referred as hidden heat? It's because when they first did the experiment, right, back in the day, they used to find that whenever you provide energy to something, temperature বাড়তে থাকে, but then there's a pause. Pause মানে কি? তুমি heat দিয়ে যাচ্ছ কিন্তু. You have not stopped heating the thing, but you'll find that the temperature becomes constant. And they used to call it hidden because they don't know where did it go. So it went somewhere because you're still providing the heat, right? That's what's called latent heat. Eventually, we realized that this latent heat that we have here is actually used for what? It's actually used to change the state of your material here. So what will this ice start to do over time? Melt, right? But will it melt right away or will it melt gradually? Gradually, right? So you'll find that initially it is size set to and what's starting to show up on the side? Liquid water. And there's more water here. And surprisingly, you'll find that at the end of the cycle, like end of this line, right? You'll find that there's only what available here? Liquid water. But what is the temperature of this liquid water? Still 0 degrees Celsius. And it's that confusion that students have, which they don't clarify themselves all the time. It is possible for you to have solid and liquid at 0 degrees Celsius. So, normally when they say something is 0 degrees Celsius, the first thing that comes to your mind, it's an ice cube, right? No, it's actually possible for it to be water as well. It is possible for it to be a mixture as well. So if you have like a ice cube here, right, halfway through here, you'll find that you have water and ice in your container, but what's the temperature of the container? 0 degrees Celsius. It is possible. But yes, when you have entirely water, it indicates what? You're at the end of the heating process. And ice at the start. And that's where your A-level questions become challenging. Not challenging, but you have to be careful. They'll say that somebody heats something and they have water at 0 degrees Celsius, which means at which part of the step are you at? Are you at the start or are you at the end, right? Our mathematics bole that the person has done half the heating process. How much liquid does he have? So turns out if the energy transfer is perfect, at the exact midpoint, you'll have exactly 50% what? Ice and 50% what? Liquid water, okay? And this ratio keeps increasing for water and ice komte thake. So right at the end, you just have like maybe a small piece of ice and the rest of them are water and there's 0 degrees Celsius water. But do you understand the transition process here? It's actually a transient. It's not like ice and then instantly water. It happens over time. And throughout that time, what is your temperature? 0 degrees Celsius. So in this particular scenario, can you tell me what's changing? So del K plus P is my internal energy, right? Konta change hochhe? Yes, so the P increases here and the K is constant. And how do you know the K is constant? There's no change in temperature. I told you temperature is the best indicator for K, right? So in this particular scenario that you see here, you'll find that there's absolutely no change in the K, but you're still providing energy, right? Where is the energy going? It's going to use for what? For breaking the bonds. The more appropriate term would be loosen the bonds because you're not literally breaking them apart. You're just taking them further apart. Okay. So yeah, that is the process. Now, this particular process going forward has a name. What is it? Melting. It's called melting. Okay. And the energy that's needed, associated with this, is called the latent heat of fusion. Turns out if you go the other way, that is called what? Freezing. And that is also the same value, latent heat of fusion. So তোমার হচ্ছে ফ্রিজ করতে যে amount of energy লাগবে, boil করতে, sorry, melt করতে same amount of energy লাগবে. Difference is one you're giving the energy, and the other you're taking the energy away. Okay. Once you reach the end of this process and you provide heat, suddenly you start to notice that temperature কি হচ্ছে, rise হচ্ছে. So temperature টা এদিকে চলে যাচ্ছে, and temperature টা বাড়তেছে, but it's not as steep as before. It's a little flat, and you need to acknowledge that. Why is it a little flat? It grafted to flat again. Because now, what are we heating? A solid or a liquid? Liquid, right? And is heating liquid easy or difficult? Difficult, right? So wouldn't it take longer time for the same rise in temperature? So you'll find that previously ice to the heat korte 10 seconds lagto, water ke heat korte in theory 40 seconds lagbe, because water has 4 times the specific capacity of ice. Okay, that one is going to take 4 times longer. Anyways, as you reach this point here, you have what here? Throughout this process, ki thakbe amar eta water. So you have liquid water everywhere. Liquid water until you reach another temperature here. What is that temperature? 100 degrees Celsius. And once you reach 100 degrees Celsius, you start to see a flat line once again. And এই জিনিসটা careful থেকো, এটা আমার diagram is obviously not drawn properly, but diagramটা actually এরকম দেখতে. Ice melting, water boiling is way longer. It's outside the screen. Okay, and it takes very long time. So if it takes 10 seconds to melt your water, it will take you 10 minutes to boil your water. It's like, exponentially longer. And that's a 3-mark question. Why? Okay, we'll get to that in a minute. But আমার গ্রাফের মধ্যে মনে হতে পারে এটা similar, but just keep in mind that আমার জায়গার জন্য আমি এটাকে বড় করছি, কিন্তু জাস্ট এরকম গিয়ে একটু হয়, তারপরে এভাবে যায়, বাকিটা এত বড় হয়. Okay, it takes very long time. And you'll notice that, when you're boiling water in your home on a pan, right, it takes time to completely boil the water. I'm talking about boil the water and get rid of it from the pan, not start boiling. So pan মধ্যে পানি আছে, ওটাকে boil করা start করলা. Yes, it will start to bubble almost instantly, but to empty it, right, it takes a very long time, right? So কেন ওইটা আমরা শিখবো. So yeah, you start with water here, and as time goes by, what happens to the amount of water you have? মানে boiling এর সময় কমে যাচ্ছে, right? It's decreasing. So where is it going? Yeah, it's turning itself into vapor, right? So you'll start to notice এখানে what's starting to show up more? Vapor. So you have steam. There's a name for it. It's called steam. So more and more steam starts to show up. And at one point of the process, you will entirely have only what? Steam. So just steam. There's no more liquid left. And then heat korle graph that part is not really part of our syllabus. It's a little complicated, that part. But it's still C. This is D. And that is E. Can you tell me what's the name of this process? Yeah, boiling. And a boiling যে টার্মটা থাকে এটাকে বলা হয় latent heat of, কেউ জানো? Latent heat of vaporization. And what do you call the reversal of this? It's called condensation. And yes, it is also called latent heat of vaporization. Same value, is just taking the heat away. Latent heat of vaporization. Right, so can you tell me in terms of K and P, এখানে কি হচ্ছিল এই যে here? Yes. আচ্ছা বুঝছি, বাট এখানে তো আমাদের যে কন্টেইনারটা, let's say 400 degrees Celsius, so 0 compared to 400 and minus 20 compared to 400 change হলো কিন্তু অত significant না. তার জন্য you're trying to say that the difference with the atmosphere কমে গেছে, মানে surrounding temperature সাথে difference তার জন্য বেশি টাইম লাগতেছে না. এখানে হচ্ছে that could be a reason, but এখানে mainly the reason is that you're heating water and water doesn't heat up as easily, and that's the specific capacity is very high. So gradient the question should be 4 times less compared to what? Compared to ice. I'm value to provide course. water টা হচ্ছিল 4200 আর ice টা হচ্ছে 900, so 1000 ধরতে পারো। So how many times more is water? 4 times more, so it will take 4 times longer as well for the same amount of energy provided. Right, so এখানে হচ্ছে, yeah, coming back to this, what increases here when you're heating the water? Kinetic energy. And again, what remains constant? Potential energy. Potential energy will only change if there's a change in what? Structure. Okay, melting volume. And then kinetic energy will only change if there's a change in what? The energy itself. So I think you can figure out key hobe. The K is going to remain what? Constant, because constant temperature, but the potential energy key for it increase for it. So yeah, this is called the heating graph. And I think I already mentioned this already, but I'll go through it one more time. It's the same for every material. তুমি যে কোনো material graph যদি draw করো for heating, it goes through this whole life cycle. It first is solid, তারপর একটা পয়েন্টে কি করবে? It will melt, তারপর একটা পয়েন্টে heat হবে, it will boil and turn itself into gas. Yes, the values will be drastically different, right? But the life cycle is the same, except for some shortcuts that some materials take. I think you have heard of them. Some materials will jump from the solid stage to gas stage. What do you call that? Sublimation. Do you know the science behind sublimation? Why does it jump? Huh? Oh, you used to know. That makes it worse. So sublimation is what? When you go from solid to gas, right? And the reason behind that is, for that particular material, this cycle requires what energy? Very negligible energy. So basically, there are some materials that are liquid state. The whole process requires very negligible energy. So they actually go through this, but they go through this instantly. And it's such a small process, right? Arta জিনিস তোমাদেরকে just বলে রাখি, এটা syllabus-এ নাই, but I know students keep asking me, so আগে থেকে বলি. There is something possible, which is this state where you can have solid, liquid, and gas all together. Have you heard of that state? There's a temperature for every material where you can be a solid, liquid, and gas all at once. Yeah, so a triple point of water জিনিসটা জানতে হবে না, but I thought I'll just share the idea with you. It's interesting. So look at this picture here. A picture দেখলে তোমরা বুঝবে what triple point of water is. So imagine this is an ocean, and have you ever seen an iceberg float on an ocean? Right? So there's like an iceberg there, right? So floating on the ocean. And let's say it's early morning, right? There's a bit of what in the air? Fog. So you can have fog, mist, right? So if you look at this picture, you'll realize what triple point is. What is the ocean? Liquid. What is the iceberg? Solid. And you have what in the atmosphere? Fog, which is what? Gas. All three coexist, right? And this can only happen at a very particular temperature. So if you've ever seen this picture, it's because that temperature was attained 0.1 degrees Celsius for water. So for water, 0.1 degrees Celsius is called a triple point at mechanism involved where it can be at 3 states at once. Okay, so yeah, this is like the example. So you can have fog, so that is basically what? Water vapor. The ocean is liquid and the iceberg is solid. All can coexist. Okay. Does volume play a role on the duration in the process of boiling? Yes. So volume is not the right term. It's mass. Mass does play a role, and we have a formula which is mc del T and ml. So the mass will play a role. Right. So we'll go through this again next class. I'll give you notes on this. Yeah. 2006 maybe.